through graphing these, and we go through graphing these a little more thoroughly than we've done in the past. There are 9 things we're going to do each time. The first thing you want to do is find any undefined values, especially vertical asymptotes and holes, which will lead us to number 2. So basically 1 and 2 will always go together. So any undefined values, vertical asymptotes and holes are examples of those, will lead us to what our domain is. So 1 and 2 go together. The next thing you want to find are the x and y intercepts. We know how to do that. We've been doing that since pre-calc. For your x-intercept, you set the function equal to 0. For the y-intercept, you just plug in 0. Then you're going to find the end behavior. So that is, again, where the beginning of this lesson comes into play. What are the ends doing? Is there a horizontal asymptote? Is there a slant asymptote? Or do the ends just go to infinity or negative infinity? Next, you are going to do the first derivative. The first derivative chart, remember, gives you where it's increasing, decreasing, maxes and mins. So 5 and 6 go together. Finally, you're going to take the second derivative, make a plus or minus chart there. That will be your points of inflection and possibly is it concave up and down. And then we plug in any extra points we might need to graph it. But this last step is to make a graph. Now your graph should include the correct concavity, the correct increasing, decreasing maxes and mins and all that good stuff. So, really 1 and 2 go together. 3 is kind of its own thing. 4, we have to think about those limits to infinity and negative infinity. 5 and 6 go together, make that first derivative chart. And then 7 and 8 go together, make that second derivative chart. And then finally, we have to put it all together and possibly plug in some points to the original function so that we're ready to graph it. Now, as we go through these examples, that's exactly what we're going to do. We're going to do those 9 steps every time. As you do your homework, I expect you to do those 9 steps every time in that order. Okay? So that's why there isn't a ton of problems. What are there, like 5 of them or something like that? Okay, so now we're ready to go. Let's start with our first one here. Now, we should recognize that this is a polynomial. If it's in factored form, that's going to really help us with the intercepts. But let's put it, let's actually multiply it all out so we can get that lead term. This would be x squared minus 2x plus 1. And then finally, we're going to get x cubed plus 2x squared minus 2x squared minus 4x plus x plus 2, which is x cubed minus 3x plus 2. Okay. So now that we have that, let's go down our list. A polynomial, by looking at this, we should automatically know that there are no vertical asymptotes or holes, because the domain of a polynomial is all real numbers. So this graph has no discontinuities. There are no holes in the graph. We should be able to draw the graph without lifting our pencil off of the page. For the x-intercept, we're going to set the function equal to 0. Now, this is where the factored form really gives us a lot of good information, because the factored form gives us the x-intercepts. So x minus 1 equals 0, and x plus 2 equals 0. And that is 1, and that is negative 2. Now, from what we know back in pre-calc time, because this had a square on it, remember, if there's an even power on it, we should expect that there should be a bounce at that location. So now we are ready to talk about the end behavior. Well, the lead term is x cubed. So we know that our limit as x goes to negative infinity of our function, our left end, is going down, and our right end is going up. So that should not be anything, so that should not be anything, you know, that should be surprising. So this says our left end is going down and our right end is going up. So that should not be a surprise. So for a polynomial, steps 1 through 4 should be pretty straightforward. Now, step 5 and 6 are our increase and decrease in max and min first derivative chart. Now, if we're going to do our first derivative chart, the first derivative, would you want to do this version for the first derivative? Or would you want to do this version for the first derivative? That multiplied out version is much, much easier to do, right? We know the first derivative of this is 3x squared minus 3. Now you can do the other one, but I wouldn't. Always think about what we learned about derivatives. What's the easiest way to take a derivative? And so get it ready to do that. Remember how when we did that one page that had all like 200 derivatives on it? Those ones, I always say, do a rewrite, make it nice. Same thing here. Use the version that's best for your derivative. And so now we need the critical points are where the first derivative equals 0. A polynomial doesn't have any discontinuities, so it's not going to have any critical points that are undefined. It doesn't have any cusps or points or funky things on it. So if we solve for x, don't forget when you inflict a square root, it is a plus or minus situation. So we have critical points of plus or minus 1. So you could have also gotten it in factored form. That would also work. So into the second or first derivative, I'm sorry, I'm going to plug in -2, 0, and 2. And then I'm just going to ask myself, am I going to get a positive? Am I going to get a negative? What am I going to get? If I plug in -2, I get 12 minus 3, which is a positive. If I plug in 0, I get 0 minus 3, which is a negative. If I plug in 2, I get 12 minus 3, which is a positive. And that leads us to step 6, which is just list increasing, decreasing maxes or mins. So it is increasing at the positive spots from -infinity to -1, and also from 1 to infinity. It is decreasing only between -1 and 1. So if we think about these points, we increase, decrease, increase. So we know that -1 is a local max. +1 is a local min. Okay, so that's step 5 and 6. Step 7 and 8 are the second derivative information. So our second derivative, we're just going to take the derivative of that nice 3x squared minus 3, and we're going to get 6x. 6x equals 0 at 0. So we're going to make a chart with 0 on it. So I'm going to plug in -1 and +1 as my, points. If you plug in -1, you get a -6. If you plug in +1, you get a +6. So this is a point of inflection. So that's a change in concavity. So our cup is going to be down. Our cup then is going to be up. Right at 0, our two cups come together. Okay. So then let's talk about concavity. Remember, 7 and 8 go together. So we are concave down from -infinity up to 0 because this spot here is negative. And then we are concave up on the other side from 0 to infinity. And then step 9, we've got to plug in points. Now we're plugging those points back into the original because that's what we're graphing. The points we have come across so far that we saw things happen. We know already that 1 is an x-intercept, -2 is an x-intercept. Oh, I forgot the y-intercept. If you plug in 0, you get 2. So we have those intercepts. In step 5, we found we had critical points at 1 and -1. We already plugged in 1, so let's plug in -1. If you plug in -1, you get 4. We also found a spot at 0, but we already have 0 is the 0.02. So let's put in some things we know. So let's actually get to the graph. So step 9 is plug in some points and get it ready to graph. Okay, so at 1, we're at 0. At -2, we're at 0. At 0, we were at 2. At -1, we're at 4. Okay. Now remember, if we know what we know about things from pre-calc. So the concavity here is concave down until we get to 0. That is a local maximum. It's going to bounce off of here because that's a local minimum, and the concavity changed. So you could even have plugged in like 2. If you plug in 2, you get 4. But that's what my function looks like. And then try to see if everything goes with it. The cup is down. The cup is up. Our left end's going down, our right end's going up. We have an x-intercept here and here. We have a y-intercept here. There is our point where the cup is down meets the cup that's up. It is increasing, decreasing, increasing. So everything about what we found should show up in the graph, or your graph is wrong, or your math is wrong. The algebra and the graph always has to match up, or one of those pieces is wrong. Okay. Now let's talk about our first one that is a rational function. So let's start at the beginning. If this function was not in factored form, it is very important that we look at rational functions in the light of factoring. So I'm going to also think about this as x squared over 1 plus x, 1 minus x. Okay. Now, when it comes to derivatives and stuff like that, I'm going to use the version that is most beneficial to me. Okay. Okay. So number 1, there is no factor that matches top and bottom. There are no holes. There is a vertical asymptote where 1 plus x equals 0 and 1 minus x equals 0. So at -1 and at +1. So that leads us to our domain. We have to skip -1. And we have to skip +1. Now, that has nothing to do with derivatives or anything. That is just what we know about functions from pre-calc, reviewing it again this year, all those things, okay? The x-intercept of a fractional function is where the top equals 0, so in this case 0. The y-intercept, you have to plug in 0, and we get 0 over 1 or 0. So both the x and y-intercept, the only spot we ever hit the x or y-axis as at the origin, 0, 0. The power on top matches the power on the bottom. So we just get to use the coefficients on those lead terms. So the left end is going to 1 over negative 1, which is negative 1. And the right end should also be going to negative 1. And that's because our lead term on top matches our lead term on the bottom. And we could do L'Hopital's rule for this one. We could do just a mixture of things to get that to work. So now here's the fun part. We have to take the derivative. So to take the derivative, I'm going to use this version right there. Okay. So our derivative is what we do for step 5. So it's going to be a quotient rule, unfortunately. So it is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay. Now, this one isn't so bad that if we wanted to, actually multiply stuff out, some good stuff happens. And it'll work out really nice if we do that. So we get, well, actually, let's just take out a 2x. So then for the harder ones, we'll see that pattern. If I take a 2x out of the first piece, I'm left with 1 minus x squared. If I take a 2x out of the back piece, I'm left with 2 negatives, which are going to make a positive, and then that x squared. So I just get 2x over 1 minus x squared squared. Now, 1 minus x is 1 minus x, 1 plus x. So I'm going to actually break it down like this. Now, because factored form is really important when we go to make that plus or minus chart. Did 1 and negative 1 work in the original function? Did 1 and negative 1 work in the original function? It did not. That's where we have vertical asymptotes. So those are not points in our domain. Remember, we skipped those? So when you make your plus or minus chart, please put open circles at plus or minus 1. They are not critical points because they're not points. They're vertical asymptotes. But you have to include them on the chart because they do break things up a little bit. But where is the top of this equal to 0? Where is 2x equal to 0? At 0. So we do have to include 0. And 0 is our only critical point. So our critical point is at 0. Negative 1 and positive 1 are just screwed up points in the original function. But you do have to put them on the plus or minus chart. Okay. So what are we going to include? We're going to include 2x. We're going to include 1 minus x squared and 1 plus x squared. Now, the squared part tells us that no matter what I do, those are always positive things. They're never going to be anything other than a positive value. So 2x is kind of controlling the show. If I plug in test values, let's do negative 2, 1/2. That would be negative 1/2, positive 1/2, and 2. If you plug in negative 2 to 2x, that's a negative. If you plug in negative 1/2 to 2x, that's a negative. If you plug in positive 1/2 to 2x, that's a positive. If you plug in 2 to 2x, that's a positive. So we know that this critical point here, we are decreasing and increasing. So what is 0? What did you say? I'm sorry. It is a local minimum. Okay. Now let's describe where this function is increasing or decreasing. It is decreasing in 2 spots, from negative infinity to negative 2. We leap across that asymptote, and then from, negative 1. We leap across that asymptote, and it's still decreasing until we get to 0. So there are 4 pieces to this graph. And then it's increasing at all the positive ones. From 0 to 1, skip across that asymptote, and then go from 1 to infinity. And then we have a local min at 0. Now, I will tell you that we are going to have a quiz over this stuff to save you time and so that you don't make funky mistakes. I'm going to give you the original equation, the first derivative, and the second derivative for the fractions. So you'll have the derivatives worked out for you. So then you just have to know what to do with those derivatives. Does that make sense? Okay. Oh.
Actually, I like that idea. Give us everything except for the derivative.
Oh. Oh.
I mean, yeah, I'm fine with that.
Anyway. Oh.
Oh. Okay, maybe not that.
Anyway, so I am going to use the fact that our first derivative simplified version is 2x over 1 minus x squared squared. That's the one I'm going to use to take the second derivative. Okay. Yeah, so it is the bottom times the derivative of the top minus the top times the derivative of the bottom. Now let's think about how we do that derivative. We're going to have a 2, the stuff stays, power goes down by 1 times the derivative of the inside, all over the bottom squared, so it would become to the 4th. Yeah. Hence why I'm going to give you these derivatives. Okay, now here's how we get this into factored form. Do you see how there's one of those is the lowest power? So we can take out one of those. Then the only other thing we could take out is a 2. Okay, so what's left? So I took out one of these and a 2. So there's still one of those left, right? You see that? Okay, I took out one. There's still one there. So that piece has one of those. Now I don't have to put a first power, but you could. Okay, now let's look at this back piece. I took out a 2 and I took out that. So I'm just left with an x times a 2 and a negative 2x times a negative. So 2 negatives make a plus, so make that a positive. Wait. And then it's really just 2x times 2x, or 4x squared. And then the bottom, let's just ignore it for now.
Me too.
Okay, so what do we got? We get 2 times 1 minus x squared over 1 plus 3x squared, all over 1 minus x squared to the 4th. I don't know. There's one of these here and 4 of these. So your final version would be that. Okay, that's your final version. That's the second derivative, yeah. Put those together. 1 minus x squared plus 4x squared, the negative x squared and the 4x squared becomes a positive 3x squared. No. Okay. No. Okay, guys. Now let's talk about our plus and minus chart. This function has no, it has no points of inflection. Okay, so there are no points of inflection. Now here's why. Because 1 plus 3x squared, if you set it equal to 0, is 3x squared ever going to equal negative 1 in the real numbers? No. So that function is there's no points of inflection, but you do need to make a second derivative chart to see what the concavity is, okay? Okay, so that's our derivative. I'm sorry. Okay. Okay. Think about how intelligent I am because of this in math. In regular life, I'm being silly, but okay, anyway. Okay, come on. We need to finish this before we go. Okay, so -2. -2. If you plug -2 into this, okay? So we're going to plug -2 into this. Oh, shit. Okay. You're going to get a positive on the top. You're going to get a negative cubed on the bottom. A positive divided by a negative, that's a negative. Okay, so that's concave down. Now, if you plug in 0, you get 2 on the top, 1 on the bottom. That's a positive over a positive, which is a positive. If you plug in 2 on the top, you get a positive. If you plug 2 on the bottom, you get a negative. A positive and a negative make a negative. Okay, so the concavity, it is concave up from -1 to 1. It is concave down from -infinity to -1, and then from 1 to infinity. So now, I know, just let's go for it. Okay. So now we're ready to graph it. So the only point we have so far, okay, let me show you what we got so far. Okay.
0, 0.
Yeah. I will.
All it asks
Okay, so there is a vertical asymptote. Let's make this -1 and this +1.
Okay, let's do that.
Okay.
Can I go back to
So, guys, listen. 0, 0 is a local minimum, and that section in the middle is concave up. So our cup is up, and that's a minimum. So what's it look like in the middle there? Like a parabola, right? So you know, if you put the concave up, and that's a local min together, I knew that that section looks like a parabola without doing anything else. I don't have to plug in any points. Okay. Now, I know that this section is concave down. So odds are we've got 2 pieces here and here that are concave down, I would guess. But because if they go like this, isn't that concave up, which goes against what we found in our second derivative? So all we have to do, let's plug in -2 and +2 to get some pieces over there, so some spots over there. If we plug -2 into the original, we get 4 over -3.